Okay, thank you very much everyone for sticking around, and to the conveners to invite me to this little session here. So I will be talking today about the breaking of cratons, but not coming from a modeling perspective, but rather from a petrological / magmatic perspective. Oops. Okay, so that's just a world map of the distribution of cratons that goes back to Wouter Bleecker from like 20 years ago. And those dark gray, dark brown areas, this is all sort of the cratons of the world. And in blue, you can already see that Wouter already sort of indicated that according to the Pangaea reconstructions, many cratons sort of have parts on different continents that have been rifted apart, which in the most simple way means that cratons are not forever, that they actually do break. And this is what this is about, because many textbooks would tell us that cratons are sort of forever and that they're sort of super stable and that nothing can really do anything to them. So the word comes obviously from the Greek word kratos, means strong. And today I just want to show you that they are maybe not as strong as we always think. So I have two examples. The one is the North Atlantic craton here with bits and pieces in Canada, Greenland, and also in Scotland. And then I go back to where Alexander just stopped and go back to the East African rift. But I will introduce you to an overlooked rift branch that nobody really talks about in Zambia, which I think has a lot of information on craton rifting. So this map just shows you the global distribution of kimberlites, and it doesn't show you any cratons, but the outline of the distribution of kimberlites pretty much gives you an idea where the cratons sit. And that in itself already tells you that the cratons during the Phanerozoic history of the Earth haven't been that stable, because if they would be stable, nothing would come through. And the kimberlites are very volatile, rich melts. They tell you that something is acting at the base of the lithosphere, at the base of the cratons. And that's sort of a different way of showing just craton instability, or sort of the faith of many cratons. So the mechanisms that can destabilize cratons, you should be familiar with most of these in blue here: plume head impingement, astenospheric flow, lithosphere foundering. And then there's this one, which is mostly overlooked. It's the metasomatic weakening. And this is sort of my area of interest. It's sort of the action of volatile, rich, percolating melts on cratonic roots. And the effect in the end of the day will be a rheology change. It's changing density, it's changing the strength, it's changing the water content of the lower cratonic mantle. And that then combined with the other processes can lead to craton destabilization. So I will be focusing on this metasomatic weakening in my talk. And for that, we need a concept in petrology, which also most people are not familiar with. It's called redox melting. So a textbook would usually tell you that the mantle melts if it heats and if it upwells adiabatically, and you get decompression melting. And this is completely different redox melting. And just to give you this diagram here, on the x-axis, this is just the carbon-hydrogen ratio of a fluid. Lots of water on this side, or lots of hydrogen, and lots of carbon on this side. And the y-axis is essentially the oxygen content expressed as the oxygen fugacity here, meaning up here you're highly oxidized, and down here you're reduced. So deeper down in the mantle, most fluids have water and methane, so it's the reduced carbon species. And if this material rises along this trajectory here, it gets more and more oxidized. We reach the water maximum, and ultimately we start to convert the carbon into carbon dioxide and get this carbon dioxide water mixture. And that is important for this concept of redox melting, because this happens in nature. We know this from diamond inclusions and other inclusions in deep minerals, that these fluids are present, because methane and CO2, carbon dioxide, have very different effects on the peridotite solidus. This is a temperature pressure diagram here. And you see two solidus curves. The red one here, that's the reduced solidus of peridotite at much higher temperatures compared to the one that has carbon dioxide in it. And what that means is, if you start to progressively oxidize a fluid, you will lower the solidus curve and you start to melt a piece of mantle without actually changing the temperature or its position. If it would be sitting here, no temperature increase required, no adiabatic upwelling required. Just by oxidizing the fluids around it, the melting point changes and this piece of mantle will melt. And this is extremely relevant to the cratonic mantle, because we know nothing really in the cratonic root starts to upwell or anything. And heating is also mostly unlikely. So this is quite important. How do we identify this in nature? Because it's a concept. We identify this in nature by having reduced magmas, such as lamproites, being followed in the geological record by carbon dioxide-rich magmas, such as kimberlites, certain types of lamproites, and of course carbonatites. So if we can see that change from reduced melts to oxidized melts, then we know that something like a redox melting was most likely at play. Okay, I'm somewhat frozen. Okay, so this is where this becomes important here at the bottom of the cratonic lithosphere, which is generally a rather static environment, but that's where redox melting becomes important. So one of the, what we think best examples for redox melting in nature is the Labrador Sea rift, and those are just 3 time slices from 160 million years all the way to modern day. And we know that there is the small oceanic branch of the Labrador Sea that splits the Archean crust of Labrador from Greenland. And by 160 million years during the Jurassic, this was a continental rift. And a lot of these very carbonate-rich melts formed here, sort of littering literally the coasts of Labrador and also Baffin Island and Labrador. And this sequence, we looked into greater detail in this a couple of years back. What we recognized was where these lamproid events, with these red stars here, and we could see that they always occurred during the Mesoproterozoic, around 1400 to 1200 million years ago. Labrador, Greenland, Baffin Island, and Labrador. And then this stopped pretty much, and during the Neoproterozoic, and then from then on also all the way into the Phanerozoic, we get these carbonate-rich melts sort of creeping into the cratonic parts of this former cratonic unit. So this we interpreted in terms of redox melting, which you can see on the right-hand side. Just to repeat the sequence on the left-hand side, we have these lamproites during the Mesoproterozoic, then Neoproterozoic carbonate-rich magmatism, and that then gets reactivated during the Mesozoic, Cenozoic, and ultimately the breakup of this craton during seafloor spreading that kicks in at 60 million years ago. And before that, we have even alkaline basaltic activity. And all of this can be explained by these phase diagrams just by essentially volatiles changing the oxidation state. This causes changes to the solidite curves of peridotite. The geotherms change, and we essentially eat the craton from the underside and produce different types of melts that then help to make this whole beast falling apart. Then there is a little bit of pressure put on, or some extension being exposed due to plate tectonics. So these sort of things have been confirmed recently by numerical modeling, in this study, for instance, here by Wang et al. And these are that modeled sort of strong craton scenarios, intermediate and weak scenarios, and especially the weak ones. And the weakness comes from this sort of metasomatic weakening. You can see how sort of the edges get softened on these cratons, and material can be eroded away, convectively removed, essentially. And that's sort of what we built our petrological follow-up models on, to have these sort of softened craton edges closer to zones of weaknesses. So just in some sort of cartoon for this particular scenario, the successful cratonic rift of the Labrador Sea, again, at the Mesozoic time slice, we have melting at the base of the cratonic lithosphere under reducing conditions. And then later on, we oxidize fluids coming in, and we make carbon dioxide-rich fluids. There's thinning kicking in, and we produce these sort of carbonatitic melts. And then this continues until we reach sort of alkali basaltic magmas, and later on normal alkali basalts, and ultimately mid-ocean rich basalts in this sequence. And I will get back to this diagram because now I'm slowly but surely switching over to Africa, and I will give you an example where we have a snapshot of just this stage, and it hasn't quite reached this stage yet. So this takes me to Africa, and on the left-hand side, you just see a seismic tomography model by Sally and co-workers, and at the 150 kilometer depth level, and it shows you sort of the cold regions that make the cratonic roots. And the previous speaker came with different cratonic blocks and having a plume, the plume effect hitting different cratonic units. But if we actually that deep down, you can see that most of Southern and Central Africa actually make one big cratonic unit. So it's very difficult to tease the different cratonic units apart, except for maybe the Tanzania craton that clearly has really suffered a lot from potentially plume impact. So all of this in Central Southern Africa seems to be connected at depth.
Sebastian, you have 10 minutes now.
Perfect. And I would like to take you to this rift branch. Those are the cratons here. This is the Tanzania craton. I would like to take you into this rift branch here. That's called the Luangwa Rift. And it's sort of the aborted or failed branch to the Malawi rift that was most successful on this side. So we are going in here, and there has been hardly any work done from a petrology and even from a geophysics point of view. So again, we are sort of somewhere here in Central Africa. You have in yellow, the East African rift system proper coming down into the Malawi rift here, and we go into this area. It's completely amagmatic except for the red star here, which are diamondiferous lamproites. And diamondiferous is important because it tells us that these melts must come from at least 150 kilometer depths. And yeah, just before I mention this, this occurs between major cratonic blocks at surface, like Bangweulu block was mentioned, Tanzania Craton, then obviously the Kalahari Craton in the south. This is all at surface reworked Proterozoic crust. And I will show you that at depths, this is all Archean mantle. So similar to what seismic tomography already suggested. So the reason why this has hardly been studied is that this is actually quite difficult to do fieldwork in this area. It's a national park for starters. And that means there's animals like leopards and lions and elephants roaming freely around, which means you cannot do any field work without actually having local guides who keep you safe and sound. So this is probably why nobody really worked there. And 3 years ago, I went there with a couple of students to actually sample these lamproites. So this is what that looks like in the map again. That's a geological map. That's the Luangwa Rift. And the sort of brown color here, this indicates a Karoo fill. Sort of those are Permo-Triassic sediments, mainly Triassic sediments filling this. And you see the lamproid field here quite prominent. This is just Google Earth, the rift flanks here, the escarpment that you've seen on the photo, and then another escarpment on this side, the Luangwa River meanders through this, and we get this lamproid field here. So this is clearly not a Cenozoic rift, it's sort of a Mesozoic rift, and one could consider this a precursor to the East African rift system that wasn't that much successful at this point in time. So the first thing to do was to actually date these lamproids because it wasn't quite clear how old they actually are, and this is what we came up with here at the bottom left. You see just sort of conventional Concordia diagrams, and to cut a long story short, these things are around 180 million years old. And if you're familiar with large igneous provinces, this is pretty much the same age as the Karoo-Ferrar large igneous province in Southern Africa and Antarctica. So that means the craton base sort of melts at the time when the Karoo plume hits pretty much all of Southern Africa. And the other important thing is that this happens right at the transition from the main Pangea stage into the Pangea breakup stage, which is then followed in blue here by a massive pulse of carbon dioxide-rich kimberlites that kicks in. So the whole concept of redox melting seems to work very well. Reduced here, melting the craton base, and then successively oxidizing and getting more and more kimberlites. Those are only African kimberlites here. So this seems to work quite well. And the connection here on the right-hand side to the Karoo flood basalts, which are all in these sort of bluish colors, the remnants of the flood basalts. And that's our lamproid occurrence. So lamproids, I don't really want to explain too much detail what this is, but they can have diamonds, so they form quite deep. They're highly potassic melts. And in blue here, you see a lot of lucite, so potassium silicate makes them so potassic. And the mineral of importance here is olivine in green. And we probed a lot of these olivines, and we were particularly interested in these xenocrysts here. Those are peridotite-derived xenocrysts. And the phosphorite content, that's essentially the magnesium iron content, is very high. You see, we go past 92 here, and that's only possible if you actually deal with depleted Archean mantle. So that means we are in some Proterozoic reworked crust, but the cratonic root underneath is actually Archean, pretty much the same as the Tanzania Craton or the Kalahari Craton. So it has an Archean root. And this is important because this allows us to calculate a geotherm for the region at 180 million years ago, when these lamproids emplaced. So we measured at high precision in these olivine xenocrysts the alumina content, which is a couple of ppm, and that allows us to calculate from the alumina content temperature, which we did here, and then we iteratively solve the temperature onto sort of known geotherms and check which one fits best. And what we came up with in our model is that this region, when the cratonic rift was in action, had still at least 42 milliwatt per square meter geotherm, most likely 40 milliwatts, so it's a proper cratonic geotherm, and projection of the geotherm onto the mantle adiabat gives us about 180 to 200 kilometer lithosphere thickness, meaning the LAB sits at least 180 kilometer deep. So this is quite a mystery, because by 180 million years, when this geotherm applies, this rift already contained 9 kilometers of Karoo sediment. And it seems that the mantle part to the lithosphere hadn't really suffered that much and is still cratonic in nature. So this is sort of what we came up with. That's sort of also coupled with some preliminary magnetotellurics data. So we have these thick blocks in the north, Tanzania, Bangweulu, then in the south, Kalahari, and we are sitting here somewhere at 180 million years, and present day probably sits somewhere here just a little bit shallower than 180 million years. And we actually sample in the diamond stability field. And this is sort of really melting, metasomatically enriched, but very reduced Archean mantle and giving us these lamproites. And the question is the story over for the Luangwa Rift? Is this failed or is this still ongoing? And I would argue this is ongoing, because if you look at this seismotectonic map of Africa, clearly you see that the western and the eastern branch host most of the seismicity, including also the Malawi Rift. But you see that there is still quite a bit of seismicity in the Luangwa Rift. So this is still eating its way south. The rift is propagating and hitting these sort of cratonic units here. And as a matter of fact, we have in northern Botswana and even in South Africa, a lot of high magnitude earthquakes that would support that view that these rift branches are all active and that the rifting story hasn't really been closed yet for this part of the world. So back to my original cartoon that was developed for the Labrador Sea Rift. So I would argue that the Luangwa Rift in Central Africa is just showing you this step here, the reduced melting in the diamond stability field, giving you these potassic lamproites. And it's just about to start to see this influx of CO2 and getting these carbonatitic melts. This would be equivalent to the western branch of the East African Rift, where we see primitive carbonatites and melts like Kama-Fujites coming through in Uganda and so on. So that's the next step. And in the Luangwa Rift, we are just stuck here at the moment. So back in the day when we did this cartoon, I started to draw rifts in the crust just at this stage. And I would need to revise this now, because I would argue that already at this early stage, we have significant rift basins, and that's quite important. So that there is really rifting activity, even though the lithosphere hasn't suffered that much at the bottom at this point. So just a summary cartoon, sort of how one could envisage this at about 180 million years. You have the Karoo plume hammering Southern Africa. A lot of the flood basalts form in thin spots here, and you get the flood basalts coming out, and the heat and also reducing fluids sort of get you these sort of low volume lamproitic melts coming through on occasions. And then if this whole thing gets more oxidized, when it lingers for long enough in the lithosphere, we start to get these carbonatitic melts and start to thin and erode the edges of the cratons. But the plume by that time probably has already retreated. And that takes me just to a set of take-home messages. Sort of, I would say that in general, plume impact, mantle flow, and metasomatic weakening, they all act in some form of concert, or they can be sort of occur successively, but all they do together is to destabilize the cratonic roots. It's the redox melting that really drives mantle metasomatism, and this metasomatism really drives the weakening of cratonic roots, which means it makes them prone to removal. You still need some form of tectonic stress to remove the root, but it's the chemical weakening that sort of really facilitates this. And point number 3 is that I would argue that substantial rift basins do form on very thick, almost 200 kilometer thick cratonic lithosphere. And that is now not just sort of numerical modeling evidence. This is actually evidence from natural samples and petrology that I presented today. So thank you very much, and I'm happy to take questions.
Thanks a lot, Sebastian. That was an impressive talk covering a lot of different cratons. Bob Trumbull, you have a question.
Hello, Sebastian. That was very nice. I agree. What do you think is the main reason for this later oxidized metasomatism? What's the oxidizing agent? What's causing this more oxidized mantle to form in the first place? Or is the reduced mantle the exception?
Well, generally in the cratonic lithosphere, is generally a profile of the deeper you go, the more reduced you go, just by a crystal chemical effect that has to do with the garnet chemistry. So meaning the deeper you go, the more reduced. And that's sort of the main reason why one would argue that deeper fluids are more reduced. And if you bring them up, at some point, they must get oxidized. And it's essentially sort of an effect of the fluids reacting for long enough and the craton essentially becoming over time more and more oxidized, sort of in the combination of these fluids coming in. And also the shallower the fluids get, the more oxidized they get. That's sort of a thing that takes time.
So it's an intrinsic process. It's not, you're not introducing something like a subduction zone into the roots of a craton during orogeny. It's something which is intrinsic to the continental lithosphere.
Yes, what I described, that would be sort of essentially intrinsic, but what you described, that exists too, and that's sort of then little excursions of more oxidized material coming in sort of periodically during continent collisions and so on. So that exists too. But overall, the background redox state, you will oxidize fluids the closer they come to surface. Yeah.
Okay, thank you. There are several questions, and I'm afraid we won't be able to answer all of them. So I would like to hand the word over to those that have not asked a question today yet. So, and that's Jeroen as a start.
Yeah, thanks. That was a very interesting talk, Sebastian.
Thank you.
Just to make sure that I understand correctly what you're suggesting. So you propose that you've got these lamproites first, the melts they create, and that they release the fluids in the lithosphere, and then those fluids do the job of metasomatism and weakening and so on. So my question here is, do you only need one stage, one event of lamproites, or one event of kind of melting, and then over a very long time, over hundreds of millions of years, that does the job? Or do you need multiple events to kind of continuously provide new material to eat into the lithosphere?
It depends. There's probably many. That's a very good point. So there's many factors at play, and for the Labrador Sea Rift, it's clearly a long history of metasomatism and then different tectonic effects, possibly even the Iceland plume playing a role, and later around 60 million years ago, and so on. The thing is with lamproites and any of the carbonatitic melts that we see at surface, in most cases, we only see the tip of the iceberg, meaning these melts have a very hard time coming through. They react out. But in theory, nothing prevents them from being there sort of permanently and acting continuously over time, and at some point just changing their nature. What we see at surface when we find intrusive rocks, dikes, date them, measure the isotopes, that's essentially just giving us an idea what might be deep down there. But we have always argued these melts are permanently there, because if you deal with these, with the redox melting concept, nothing really hinders the cratonic base from constantly being soaked and melt, right? At very low degree melt that is essentially not detectable by geophysical methods. Yeah. And sort of the metasomatic nature of most peridotite xenoliths sort of confirms this. There's hardly any xenolith that isn't really metasomatized.
Okay.
Yeah, but from anything from long term to very quick and short term, this can all happen.
Okay, yeah, thanks.
We're running a bit out of time, but since you're the last speaker and won't have time to ask the questions in the chat, I would like to hand the word over to Stuart for the last question, and then I wrap it up.
Thanks, and apologies, because I'm probably going to follow on really from what Jeroen was asking, because so the North America example, you had, was it about sort of between 600 and 800 million years between the lamproite and the sort of carbonatite kimberlite activity. So it was really just trying to understand that question of, if this is happening everywhere where we've had this, kind of why doesn't it happen absolutely everywhere, and why do we still end up then with cratonic bases that don't have this happened and haven't been weakened to this extent? Yeah, so most of this, what we describe probably, and that's also what the modeling shows, that the numerical modeling is happening closer to the craton margins. So beneath proper cratonic roots,
it's probably less likely that something like that happens. But then the center part of a craton is a pretty small area, and most of the craton is essentially marginal material. And that's where this activity happens. So that's why you wouldn't find it in any craton. And the other thing, the concept of exploration, I've been working for a couple of years in mineral exploration and diamond exploration. You should never assume that already everything was found. Otherwise, like we deal with very small volume melts, and pretty much any craton where I went, we have always discovered new magmatic pulses of lamproites, carbonatites, kimberlites. So one should sort of, the picture is for some cratons more complete than it is for others, but there's potential for discovery, which sort of drives essentially exploration.